Step 1. The most important first step in solving these problems, and honestly most thermodynamics problems, is writing down what's known and what's unknown, or in other words, what you need to find. Importantly, as I mentioned earlier, some knowns are implied conceptually by the constraints given by the problem statement. So let's go over some common constraints that you'll find in these types of problems. So the first one is rigid tank, which basically means that the container volume will stay constant throughout the entire process. The next one is if the problem says that the system is insulated or adiabatic, that means no heat exchange will happen with the surroundings. In other words, you can assume that no heat, represented by Q, will come in or out of the system. If the problem says that the valve is left open, that means the final pressure inside the control volume equalizes with the surroundings if the valve is open to the surroundings. If the valve is between two tanks, that means the pressure equalizes in both tanks. If the problem says that the process is isentropic, which is a concept that you've probably come across in class or in lecture, and if you haven't, you definitely will because it's really important. But it basically means that the initial entropy equals the final entropy. In other words, the overall change in entropy is zero. If you come across a freely moving piston device, that means the initial pressure will equal the final pressure, because the piston is regulating the pressure throughout the whole process, even if the volume changes. If no velocities are given, that means you can ignore the contributions of kinetic energy, since we know that kinetic energy involves velocity. And if no height changes are given, that means we can assume no contributions of gravitational potential energy. The next step is pretty simple. We just need to determine if we are using rates or not. And this will be pretty clear in the problem statement because the givens that they give you will involve rates or not. If we do use rates, that means we're going to be using mass flow rate, which is m dot, heat flow rate, which is q dot, and power, which is w dot. And notice they're all in terms of units per second. And if we're not using rates, then we can just use mass, Q for heat, and W for work. For the third step in solving these problems, we want to find the thermodynamic state of the system, which you're probably familiar with if you've been in thermo for a certain amount of time. This is where the tables come into play. So you were likely given a property tables booklet of some sorts when you signed up for the course. And in a general sense, it's really just a relationship between intensive properties in relationship to certain temperatures and pressures. And we can use these properties to determine whether or not the initial and final states of the system are in a superheated state, a saturated mixture state, or in a subcooled or compressed liquid state. And if the values that you need aren't given in the table, then you have to interpolate, which everyone loves to do. Step 4 is to always write down the first law of thermodynamics for transient problems. This is really the spine and backbone of the solution. Assuming states and not rates, the first law tells us that the energy in minus the energy out is equal to the delta, or change in energy, of the control volume, which is usually just the container in which holds the mass or has mass flowing through it. We know that the change in energy of a system is equal to the final internal energy minus the initial internal energy. So this is the general way of writing the first law of thermo for a transient problem. And this is really just the overall general conceptual way of thinking about it. But when we actually want to solve the problem, we want to write it in a sense where we can use heat, work, mass, and intensive properties that are either known or that we found in the tables, or that we're trying to find that are unknown. I know it looks like a lot, but just to break it down a little bit, the first law tells us that energy in minus energy out is equal to the delta E of the control volume. So when the energy in will always be heat in, work in, and mass times the intensive enthalpy plus potential energy plus kinetic energy. These values are either given to you or we have to solve for them. And it's really the exact same thing for energy out, except it'll be Q out, work out, plus the mass out times the intensive enthalpy out, intensive potential energy out, and intensive kinetic energy out. And you may have seen this right here being called theta. And so this will be m theta. But just to keep it, as useful as possible, I always just write it out. I don't write the theta step because unless it's explicitly asked for in the problem or your professor wants you to explain it conceptually, there's really no point because they equal the same thing. For the right side of the equation, the delta E of the control volume, we know that big U, which stands for internal energy, equals mass times intensive internal energy. And so we just write, this should be final right here, mass final. So mass final times intensive internal energy final minus mass initial times intensive energy initial. I know it sounds it's a little convoluted, but this is just think of this is the final mass and intensive energy. This is the initial mass and intensive energy. This is the energy coming in, which is different from initial. This is the energy leaving the system, which is different from final. So that's really the two distinctions that we need to understand conceptually is this is energy coming into the system. This is energy coming out of the system. This is the final state of the system. This is the initial state of the system. So it's coming in and out, and then there's final initial states. Down here is just to clarify, I'm sure you know, but Q equals heat, W equals work. PE is the intensive potential, which we mentioned earlier, which is just the gravitational constant times Z, or the height. And KE is the intensive kinetic. You may be familiar with kinetic energy as being 1/2 V squared, but I always write it because when you do the unit conversion going from joules to kilojoules, it ends up being 1/2000 times velocity squared. Since most values are usually given in terms of kilojoules, I always just save myself the headache and always write it in terms of kilojoules. But that's just a personal preference. If you want it to be in joules, you would have to do 1/2 velocity squared. And as I mentioned earlier, mu is just equal to mass times the intensive internal energy, which we find from the tables. And as I said earlier, if we are working with rates, then all we have to do is change Q, W, and M to being the rates version, which is Q dot, W dot, and M dot. Everything else stays the same. And I like to write the first law out like this explicitly every time because it shows us exactly what we have and what we don't have, or what we need to find. For example, if the problem says that the control volume or the system is adiabatic, that means we automatically know there will be no Q in or Q out, and we can cross those off immediately. Similarly, if there's no work being done to the system or by the system, then we can automatically cross off work in and work out. So it really just helps keep everything organized and makes the problem simpler to solve. So with all that being said, let's take a look at an example and see how we can use this framework to actually solve a real problem. All right, let's take a look at this example. So two rigid tanks are connected by a valve. Tank A contains 0.2 cubic meters of water at 400 kilopascals and 80% quality. Tank B contains 0.5 meters cubed of water at 200 kilopascals and 250 degrees Celsius. The valve is now opened and the two tanks eventually come to the same state. Determine the pressure and the amount of heat transfer when the system reaches thermal equilibrium with the surroundings at 25 degrees Celsius. So right away, we have rigid tank, which I mentioned earlier, connected by a valve. So we know that the volume of tank A and tank B will not change. They will stay constant. They tell us that the valve is opened and is left open because it says the two tanks eventually come to the same state. So sometimes it'll tell you that, sometimes it won't. If it says it's left open, that means they will come to the same state. But in this case, they tell us outright, which is nice. So initially, we're given that the volume of tank A is 0.2 meters cubed. And just to clarify, the V with the slash through it means extensive volume, or volume that is dependent on mass. In this case, that would be the given volume since it's the total volume of the tank. But V without the slash is intensive volume. So if it was given in terms of per unit mass, and I would use a V without the slash. But I just do that because the V, uppercase V and lowercase v, sometimes are hard to differentiate from each other. So it kind of just helps keep track of what's intensive volume, what's extensive volume. Anyways, moving on, we know that pressure A is 400 kilopascals, and that the quality is 80%, which equals 0.8. The volume of tank B is 0.5 meters cubed. Pressure of tank B is 200 kilopascals, and the temperature of B is 250 degrees Celsius. So this is kind of just personal preference, but I like to have everything pertaining to one aspect of the system or control volume in one column, similarly in another column, just to keep everything organized. And so we know that the final temperature is 25 degrees, and we want to know the final pressure and the heat transfer of the system. So right away, we can tell that we're not being asked to find power or any sort of rate. So we know we're using states. And right away, we want to find the thermodynamic state of the system initially. There's different ways you can do this, but so I like to do is, do one of these little bracket things and just write what it is. Or you can do it down here. But right away, we know that since we're given an X or a quality value, that this is a saturated mix. It has to be. And for determining the state of tank B, we can look in the table. We can either look at the pressure or the temperature. In this case, I went and I looked at the pressure at 200 kilopascals, and I saw, okay, the T sat at pressure B, which is 200 kilopascals, is 120.21 degrees Celsius. So right away, we see that the temperature of B is greater than T sat at the pressure B, which means this is a superheated vapor. So the temperature at B is hotter than the saturated temperature at 200 kilopascals. So we know that it's superheated because it's hotter. So looking at this problem, we know we want to find the final pressure, and we're given a final temperature. So we can assume we want to compare a final value with our final temperature in the tables, because if we go to the tables and we see T equals 25 degrees and we have a line of data, if we have something to compare with that line of data, then we know what the state of the system is, and that will help us determine the pressure. So right away, I notice we're given volumes. So maybe we should try to convert the volumes that we're given into intensive volumes. And we know the total volume of the system since the tanks are rigid, and we can find the total intensive volume of the system and compare that to the final 25 degrees Celsius that we're given. So we know that in order to find mass, we can use the fact that extensive volume divided by intensive volume gives us the mass. And in a general sense, we can see it like this. So if we have meters cubed in the numerator over meters cubed per kilogram, this equals and we get mass. Because when you have a denominator in a denominator, that gets moved to the numerator. We can find the intensive volume of A by using this formula. V of a mixture is equal to VF plus X times VFG, which you've probably seen by now. VF is the saturated liquid value of volume at a specific pressure or temperature. VFG is the saturated vapor minus the saturated liquid value of volume at a specific pressure temperature. So doing this, VA, we're given a pressure, so we can say at PA is equal to 400 kilopascals, just to make our logic clear to a professor who's grading or for our future selves. We can plug in the numbers, which I have in front of me. We were given the X, and then for volume, sometimes you have to do a difference between two numbers because they don't give you it directly. Let me just move this over. And we get 3.7 meters cubed per kilogram. All right, and that's just a way to stay organized, lay out all your thinking, why you're writing down what you're writing. Now, thankfully, since tank B is a superheated vapor, we don't need to use this equation. We don't need to interpolate. We know that V of B equals V at TB PB equals 1.19 0.89 meters cubed per kilogram. When something is superheated, all you need is a pressure and a temperature, and you can get all the values you need from there. You don't need an X value because there's no mixture. So in order to find the mass of A, we can use the formula that we discussed earlier, and we know that the given volume is 0.2 meters cubed, and then the intensive volume that we found earlier is 0.37 meters cubed per kilogram, and then that equals 0.54. Similarly with B, we were given 0.5, and we found VB, which is 1.199. Rounding a little bit, but I don't round in the calculator. I just, when I'm writing, because I get lazy and I don't want to write it. All right, now we have mass A and mass B. So you might be wondering, well, why do we even find the masses to begin with? Well, we know that intensive volume is equal to meters cubed per kilogram. So if we have the total extensive volume over the total mass, then we can find the value of the intensive volume of the whole system in the final state. So doing that, we know V total will be VA plus VB. M total is MA plus MB. And plugging that all in, we get the intensive volume of A and B at the end. So now that we have that, we know that T final is 25 degrees. So we go to the water tables, we go to 25 degrees, we look at the data, and we see that volume, the intensive volume AB that we found, lies in between the VF and VG values at 25 degrees. Therefore, not only is it a saturated mixture, but P final, let me move this, is equal to P sat at T equals 25 degrees. So we can say with certainty that the P final is 3.17 kilopascals. All right. And so that's how you find the pressure. Now, in order to find the heat transfer, this is where the first law of thermo comes into place. So let's write the first law, E in minus E out equals delta E the system. And we know this means that Q in plus W in plus M times H in. And as we discussed, if there's no contributions from potential and kinetic energy, then we don't need to include it in the equation in writing the first law. You can write it out and then cross it off if you want, but just for the sake of saving time in writing, I'm just going to leave it out since we weren't given a velocity and we weren't given a change in height. So that's how we know. So we have the E in. So we know there's no work being done. There's no mechanical work being done. The boundary isn't moving. There's no work being done by or to the system. We can immediately cross that out. And we know that these two rigid tanks are connected to each other. The system is closed. So is there any mass moving in or out of the system? There's not. So we can immediately cross off MH in and MH out because there's no mass coming into the system carrying energy with it. And there's no mass leaving the system carrying energy with it. So we don't have to worry about those terms either. And in terms of Q, there's either Q going in or out at the end of the day. We know that because it said it did, and then it's also asking for this. So we can make an assumption, and if we're wrong, we'll still get the same right number. It's just, it'll be a negative if we were wrong. So I'm gonna assume, since the temperature of the surroundings is colder, the surroundings are going to pull heat from the system. Therefore, the heat will be going out of the system into the surroundings. So I'm going to assume no Q in and that the Q will be leaving the system. So I'm going to leave Q out in the equation. So right now, I want to focus on this important part. We have M final, U final, minus M initial, U initial. So let's break this down because it's not as clear as it might seem. So what does the final state of the system look like? Well, the valve is left open and the two tanks are freely able to interact with each other. So we know that the final mass is Ma plus Mb. The final internal energy is also A plus B, because all the mass is interacting in one big system. However, initially, the valve is closed. The two tanks aren't interacting. The mass is within each individual tank. So we know initially the internal energy of A does not equal the internal energy of B. We have to treat the energy contributions separately. So we write it as the mass of A times the internal energy of A plus the mass of B times the internal energy of B. And this is all initial. If it's a little confusing, just think of it as the tanks are separate. We need to calculate the amount of energy in each tank separately. In the end, it's just one big tank. The amount of internal energy is uniform and is being contributed to by all the mass all at once. So putting this together, if we move this negative sign, which is being attached to this Q, over to the other side, which is really just down here, then we know that Q out is equal to just simple algebra, distributing the negative and flipping the order. So we already calculated this. We calculated this. We know this. It's just A plus B. All that's left to do is go to the tables to find U of A and U of B. And we already know the final state. So to find U of A plus B, we know that it's a saturated mix at 25 degrees, which we use to find the pressure. U of A is equal to U of F plus X U of G at the initial pressure, X equals 0.8. We can calculate that. And then U of B is, we can calculate that, and then So the last thing we need to do really is just find the quality, or X, of the saturated mixture at the final state. Yeah, it's really quite simple. I mean, we found the intensive volume earlier. And so we know that this equals VF plus X VFG at T equals 25 degrees. And solving for X, we get V of AB minus V of F, just doing algebra, over VFG. T equals 25 degrees. So we go to the table, we plug all those numbers in, and we get 0.01685. So we plug that into there. So this equals 143.7 kilojoules per kilogram. This equals 2731.4 kilojoules per kilogram. And this equals 3.3 kilojoules per kilogram. And there you have it. Plug all that in. Now it's just plug and chug. So you have the masses from earlier, and we just found all the intensive internal energies. And we find that Q out is equal to 2170 kilojoules. And we can see that our assumption was correct. The number is positive. So the heat was leaving the system. And there you have it. It might seem a little complicated or convoluted at first. I think the hardest part is just recognizing where the internal energy contributions come from. Just think about where the internal energy is coming from in terms of mass. If the tanks are separate, then the mass in each tank has its own internal energy. We have to treat those as separate. If the tanks are connected, that means all the mass is connected in the tank, and we can treat the whole system as having one internal energy state. So yeah, the hardest part of these problems is really just keeping track of everything and making sure you're choosing the right data values from the tables, keeping your subscripts organized and cohesive. But hopefully this video helps you understand these kinds of problems better. I know they can be pretty tricky, but I'm always here to answer any questions. If you have any questions, feel free to leave a comment or hit me up on Instagram or whatever. I'm always happy to help. And yeah, this class is important. So, but it's not as, I feel like it's not as hard as you might think once you kind of do some problems and get familiar with it. But like any other engineering class, you really just have to do practice problems and spend the time to really understand conceptually what's going on. Anyways, thanks for watching. Hope it helped. Good luck with your studies. See ya.